You know I'm going to give them to you. You know I'm going to give you these example problems, and we're going to do them over and over and over and over and over until I force you to have fun with them. Yes, that's what we're leading into. And this example is going to be six examples. So this question says, how could the following compounds be prepared using an alkene as one of the starting materials? So it's not really telling me what else I can bring in. It just says use an alkane. So I know that I'm going to have to use a double bond. And we're going to use only really the three reactions that we've talked about up to this point in order to make these products. So I'm going to switch my screens. I'm going to clear this out. And we're going to focus on one at a time. So in the very first one, they give me this ring structure. It's okay. No big deal. I treat rings no different than anything else. And I need to know, how can we make this? That is my product. And I'm going to have to figure out how on earth I can get to that from a double bond. Okay, so let's think about this backward. That's how we do it. So I look at the group that's there. And what I see is this group that's OCH3. Okay, well, there's one group, OCH3, and I know that the other group was probably a hydrogen, because that's all that we've done really up to this point. We've added hydrogen on one side and the OCH3 in this case to the other. So I know that these two things are going to come together and we are going to have an alcohol reaction in order for this thing to work. Now I've got to figure out where that double bond is going to be located. Well, this OCH3, it's got to be attached to one of the sp2 carbons, right? That's kind of what we've always been saying at this point. So this carbon has to have a double bond. Folks, it doesn't matter if it goes up or if it goes down. It's the same no matter which direction that you go. If you go up, it's a CH2. If you go down, it's a CH2. Who cares which way that you draw it? But you've just determined in doing that what type of alkene that you have, and it's this one. So I take cyclohexene and I'm going to react it with methanol, and I will end up getting the cyclohexyl methyl ether. Let me name that again. Cyclohexyl methyl ether. That is the common name for that ether structure. If you do not like that, we can name it a different way. We name the long chain first, and this is cyclohexane. And then on carbon number 1, I have the methoxy group. So meth for one carbon and oxy for oxygen. So methoxy cyclohexane would be an acceptable name for that compound. That is how we end up with that product. All right. So yet again, another synthesis problem. This is where people tend to break down on me a little bit because they have a little bit of trouble seeing what could they start with in order to get to where they're going. But this is the surefire way to do it every time. Look at what group is there, identify it, know that a hydrogen probably came along with it as well at this point. That group has to be on a carbon that has a double bond with it somewhere. And that is how we determine that that was the starting alkene for this reaction. All right, so let's do another. This one for B, CH3, oxygen, carbon, another carbon, CH3. Up here, CH3. Down here, CH3. Okay, so we need a starting reagent. I need to figure out what else I'll react with it, alkene-wise, in order to get this product. So this is what I'll do. I'll look at this OCH3 group and I say, look, right there. Right there we go. So I know that this is a CH3 group that was probably added on, and I also know that it has to be a hydrogen probably come along with it. I've just identified one of my reagents, didn't I? This is a CH3OH group. It's got to be methanol. I've reacted methanol somehow. Okay, well, that group has to be on a carbon that has a double bond. Well, it's the same no matter which way we go. If I go up, if I go across, if I go down, it all goes to a methyl group. It doesn't really matter. So I'm just going to draw the double bond somewhere, some form, some fashion. So there we go. There's my double bond. There's my alkene. Well, just to make it pretty on a sheet of paper, I'm going to slightly turn this around. Okay, I'm not going to draw this straight up and down. I could. I'll give you credit for that. It's no big deal. But I'm just going to rewrite this in a different way. This is a CH2 group that's double bonded to that middle carbon. And then that carbon has a methyl group that kind of points up and one that goes over right-handed. So I've just kind of turned it and twisted it a little bit. That's all I've done. However, if you want to keep it in this orientation because you think that's easier, do it. I don't care. So there's one possibility, right? And if you gave me this possibility, that is correct. You did a good job. I've got an alkene to the left, and I have alcohol to the right. But some of you might not have done that. Let me erase this. Some of you could have said, well, here's the group that comes with the O piece. All right. Okay. So this is the O group that has all of this mess with it. And then you would have looked at this and said that also has to have a hydrogen. Okay. So instead of a methanol, you would have chosen a tert-butyl alcohol. I mean, that's what that group is. That's not a problem. That's not the problem. However, what you have left over with here is just one carbon that's left. How are you going to form a double bond between one carbon? You can't do that, can you? No, that's silly. You can't do that. So because of that, this is not a plausible choice. It specifically told you had to start with an alkene. Well, if you chop this molecule in half at that location, and you want this to be your alcohol group, that's great. No one said that you can't do that. But over on this side, there's no way that you can get a double bond from that. It's just one carbon, and that's it. If there were two carbons there, you could have. But not with one. So this is the only possible choice that we could get for part B of that problem. Next, CH3, CH2, oxygen, CH, down here, CH3, CH2, CH3. So we got to pick out an alkene, and we got to pick out an alcohol, probably, for this to work. All right, well, I'm just going to pick the smallest alcohol first. I mean, that's normally what I do. So there's the oxygen, and let's just pretend like this is the group that we added on right there. So this is a CH3, CH2O, and I know that the other piece had to be a hydrogen to come from that. So I know that ethanol probably is going to be a choice in that method. So I'm going to write down ethanol. There we go. All right, well, if this oxygen's attached to this carbon, that means this carbon has to be part of the double bond. All right, does it go left-handed or does it go down? Okay, well, you've got a choice here. You've got a choice. Let's just draw it down. Let's put that double bond in the very first position. So CH2 double bond CH, CH2, CH3. Now, you're probably wondering, well, I thought you told me you were going to draw it down. I did, all right? And then I just straightened it up a little bit. I know this might be a little bit confusing, but that's what I did. So if this is the carbon that's going to be involved in the double bond, I'm going to have to go to a neighbor down below, and I'm going to have to get rid of a hydrogen there, so that way I can draw the double bond between those two carbons. And then I just took the kink out of it. That's all that I did. I just took the kink out. Well, that was one choice that you could do. The other choice is not to target the bottom. The other choice was to go this direction with it and erase one of these hydrogens. Okay, well, we can draw that choice as well. This is going to be a CH3. Then that goes to a CH that's double bonded to a CH and then a CH3. All right, well, that's possible too. No one says that you can't do that either. Well, the directions here just say how could they be prepared, and they're assuming how can you best prepare them. Well, either one of those are okay. All right. But there is a difference on which one would be better than the other one. So if the question just randomly said, how could you prepare it like this one did, then these choices that you have just drawn on a sheet of paper, any one of those would have been fine with me. But if the question said which one would be the best way to prepare it, there is a difference between these two. Let's talk about the differences. If this double bond broke and I get a single, I've got a carbon to the left and a carbon to the right. Well, my hydrogen from the alcohol group would come in first, and it would automatically go to the one on the left. That's where the most hydrogens are. This would be regioselective, and it would give me that OCH2CH3 on that second carbon, which is what we want. Down here in the other choice, well, if I look at that one, my double bond's going to break. My H goes on first, either to the left or to the right. And in this case, it doesn't really matter. It can flip-flop back and forth. And then the OCH2CH3 would go on next. Some cases it would go over here. Some cases it would go over there. Well, folks, it doesn't matter. If it goes left-handed, it's still in the second carbon. And if it goes on the right-handed one, it's still on the second carbon. So both of these choices are as acceptable as the other one, even if the question said, what's the best choice? Because either which one of these would end up with the correct one. Where we would have had a problem is if they would have added an extra carbon onto this chain. Then it would not be symmetrical anymore. Then we would be forced to choose the first one, because that would be the surefire way in order to get that OCH2CH3 onto that second carbon. All right, so either one of these, perfectly fine. Now, the other question is, I would have some people that would not choose either one of those. All of those are correct answers. But they would have looked at this problem and they would have not pulled that alcohol group off to react with. They would have looked at the other half of the reaction. Can you do that this time? Well, let's take a look. What if this was the piece that we added on? All right, this was the alcohol piece right there. Well, that means that this oxygen would have had to be on an sp2 carbon, which means that that had to have a double bond, and it can. I get a CH2 double bond to a CH2. There you go. So in this case, it does have another carbon that it can form a double bond with. That's okay. That's fine. And then on the other side, I have this oxygen with a CH, CH2, CH3, and then down here a CH3, and that could be my alcohol group. Look at there. No, sorry. That's going to be just one hydrogen. I got a little crazy. There you go. That would have also been okay. Not a problem. Whatever works. And look, I even went crazy down here as well. That doesn't make any sense. I've been doing these videos too long. I'm going crazy. All right. So there we go. So either one of those would work. Either one of those choices in the first round or second round would be okay here. Again, tons of different options that you can use to give me a correct answer with these problems. Not a big deal at all. Let's look at D. CH3, CH, CH2, CH3, and off of this I have an OH group. Let's do this one a little bit faster. I need to know what alkane that I need. Okay, well, I've got an OH group that's here, right? I'm going to write that over to the side. So I'm going to erase this OH group and that bond, and then I choose one side or the other, and I have to ensure that it's going to go where it's going to go. I'm going to choose the left-hand side here. That is where my double bond is going to end up going. That means I need to take a hydrogen away from that side, and there we go. So I'm going to take this, I'm going to react it with a little bit of water and acid, and that is a way that I could get that alcohol that this problem made us start off with in the very beginning. If that double bond breaks, we are ensuring that the H goes left-handed for sure, and then the OH will go to the right-handed structure instead. All right, that one went a little bit faster, and hopefully these others will as well. I'm going to kind of chop some of the fat off of my lecture explanation here just to make them go a little bit faster. All right, so here's the molecule that we want now. What alkene do we need to use? Well, that's an OH group, so I'm going to write that up to the side so I don't forget it. I'm going to erase that OH group. I'm going to erase that bond that was there. I know that that carbon had to have a double bond somewhere. I'm just going to draw it there, and there we go. I'm going to take that alkene, react it with water and acid, and then all of a sudden I can get that cyclopentanol, which is the product that they wanted. All right, next one and the final one is CH3, CH2, CH, CH2, CH2, CH3, and then off of that is going to be an OH group. Okay, so over to the side, I'm going to write OH so I don't forget it. I'm going to erase this OH group. I'm going to erase that bond, and I know a double bond is either going to happen to the left or to the right. I'm going to pick the right-hand side. The reason that I do that, and I get rid of that hydrogen, the reason that I do it is because it makes it a very symmetrical molecule. So when this double bond breaks and I add the water and the acid to it, well, that double bond breaks. Hydrogen at this point has no preference. It can go to either side. And whichever way the oxygen goes with the OH group, it's going to end up with the same product. I'm always going to get the OH group on that third carbon. If I put it to the left, that's the third carbon in from the left. If I put it on the right, that's the third carbon in from the right. So making this symmetrical will give me that product that I want every single time, no matter what. Okay? All right, next example. Propose a mechanism for the following reaction and use curvy arrow mechanisms when you can. Oh, okay. So it looks like they have taken an alcohol in the left. They've given me a double bond here in the center. And they're making this H2SO4, so this is a protonated version, which is good. That's what I've been seeing. And they want me to end up with what we see over there on the right-hand side. Whoa, right? That looks pretty complicated, but it's not. You use your words. Use those examples that we've done. The protonated piece makes this the electrophile. Okay, that's the purpose of the sulfuric acid. So I can take my curvy arrow now at this point, and I can take this double bond, and I can draw it to the H and pull that hydrogen off. This opens up the carbocation, and that will give me a CH3 carbon single bond CH3, because that's where that hydrogen went, played with other hydrogens. There's my carbocation. And then this big, long alcohol that came into the picture. I'm just going to redraw it. That's kind of how it started. It's neutral again. It's happy. It's minding its own business, but it still has those free sets of electrons that are there. So I'm going to take those free sets of electrons, that's a negative area, and I'm going to draw it to that particular carbon right there. When I do that, the next part of the mechanism will open up. That gives me CH3, this carbon. I'm just going to draw it the same way, just so I don't confuse you. No big deal. OH, and off of that oxygen is a CH2, a CH2, a CH, a CH3, and a CH3. Well, that's all right. This oxygen's now positive. Doesn't like it. What can take care of that? Well, another alcohol group. And this time I'm just going to write ROH. You know what that R represents? The R represents this entire thing right there. That is what R is going to represent here. Well, this is a free set of electrons. Those electrons are attracted to that hydrogen. The bond between the O and the H, that oxygen gets those electrons as well. And now we get a rearrangement that begins to happen, and we get that product. Doesn't quite look like that product, but it is. It's just a different drawn. It's differently drawn on a sheet of paper. So CH3, CH3, CH, CH2, CH2O, CH3, CH3, CH, CH2, CH2O. There's the alcohol group, and then that's attached to a carbon that's tertiary, and that goes to a methyl group on all sides. So there's the multiple steps of that mechanism as far as this example goes. So that's where I'm going to stop this video. Okay, this is getting a little messy, right? You might be getting to a point where you're pausing me and you're thinking, what did he just say? Or he might be going too fast, which is the good thing about YouTube. You can slow me down or speed me up double time if that's what you want. Or it might take one or two explanations of hearing it again and again and again for you to get it. But folks, that's the wonderful thing about pre-recorded lecture videos. You can watch me whenever you want to watch me, as many times as you want to watch me, and if you didn't get it the first time, you go on and you watch it again. And maybe that second time through, you will hear something that would trigger and that will say, hey, well, that kind of makes sense at this point. All right? So in the next example, we're going to get even more dirtier. The waters are going to get muddier. And that's because we need to talk about rearrangement. Rearrangement can happen in these problems, and we need to talk about what that rearrangement is. And that's what we'll do in the next video.